So to start, let's take an ordinary function. Let's just, for the sake of simplicity, pick some basic linear function. And we'll call this f of x is equal to 2x. This is something that we can graph fairly easily. We'll have an x-axis and a y-axis, and we'll have a straight diagonal line, y is equal to f of x. And on here you could imagine some points. Let's just say, for example, we have the point x equals 2, which would route to 2 times 2, which is 4, y equals 4. And if I were to ask you, what do you think the limit of this function is as x approaches 2, you could probably pretty quickly tell me that the answer would be 4. The reason being, whether or not you approach this 2 from the positive x direction or the negative direction, you are going to get y values that get closer and closer to a value of 4. This concept, which is pretty intuitive on its face, seems like it would be something that would be hard for mathematicians to codify, something that would be difficult to define precisely. And that's going to be the subject of the video today. How exactly were mathematicians able to take an intuitive concept like this and formalize it, codify it, so that it could be proven more stringently where those limits do exist or where they do not exist. A concept like a limit seems like something that would be difficult to define, and indeed the formal definition, at least to me, seems a little bit confusing when you first look at it. It goes a little bit something like this. We say that the limit as x approaches any value, say a, of a function, say f of x, is equal to some value, we'll say L, if for any value of epsilon greater than 0, there is some value delta also greater than 0, such that the following inequalities are both satisfied. Absolute value of f of x minus L is less than epsilon, and the absolute value of x minus a is less than delta. Now this at first seems pretty complicated. We can get into what this means by first talking about these inequalities and what it means when you see something like this absolute value is less than some value. Let's do that. Let's take this one, and instead of delta we'll just use any sort of number. I'll just say 3. And we can actually solve this inequality for x to kind of get a sense of what these inequalities represent. So we would say that this inequality is satisfied if x minus a was less than 3, and we would also say it's satisfied if negative x minus a was less than 3, reason being that the absolute value would undo this negative. It would be the same thing as this top one. Solving this for x is pretty simple. You just add a to both sides. You get x is less than a plus 3. Here you divide by negative. Remember to flip the sign. Get x minus a is greater than negative 3. And then you solve for x. X is going to be greater than a minus 3. And so if you put both of these inequalities together, you'll see that x will satisfy this inequality as long as it is greater than a minus 3 and less than a plus 3. And so what does this mean? This means that x is the interval of numbers that are within 3 units of the value a. On a number line, for example, you'd see that this would be, if you had a right here, here you had a plus 3, here you had a minus 3. This inequality would be true for any value of x that lays on this interval within 3 units of the number a. So that's what these inequalities mean. But what does this mean with regards to our definition here, our formal definition of a limit? If we take a look at this inequality, this one is telling us that f of x must be within epsilon of L, and this inequality tells us that x must be within delta of a. And if we think about this graphically, we can draw out a little graph here. Just do our x and y axis. We have x, we have y, We can think of another simple linear function that might be easy to understand. Y is equal to f of x. And we could think we would have some proposed point here, a, and some proposed limit associated with that point, we'll call L. We could think of this like there are bounds L plus epsilon and L minus epsilon. And then we could think there are some associated x values with those bounds, a minus delta and a plus delta. And what our formal definition of a limit tells us is no matter how small this epsilon value gets, meaning no matter how close we want to define y values to approach this proposed limit value, epsilon can be 1 times 10 to the negative 9th for all that matters, which would be extremely close. There will always be some associated values in the x domain which will, when plugged into our function, route to those values in the y domain that will be given within delta of the value a. No matter how small epsilon gets, there will always be some values within delta of a that, when plugged into the function, will yield y values within epsilon of our limit. And if that's true for all values of epsilon, if there will always be some value of delta that will make both those inequalities satisfied, then we say that the limit exists. And if that's still confusing, we can look at an example, and taking a look at how this example is actually applied, or how we apply this definition to a real example of a function, should let all those puzzle pieces fall into place. So let's do that. Let's start with a simple function. We can actually use the same one from the beginning of the video. I'm going to use y is equal to 2x. Or I'll say f of x is equal to 2x. F of x is equal to 2x. You can plot that. Y is equal to f of x. And we have some point here, say 2. That's associated with a y value of 4. And we want to prove, we're tasked with proving that the limit of f of x as x approaches 2 is equal to 4. And now, armed with the formal definition of the limit, we have the tools to do that. If we want to prove this, then we have to show that for any epsilon greater than 0, there will be some delta greater than 0 such that the absolute value of f of x minus L less than epsilon, and the absolute value of x minus a be less than delta. This is our formal definition of the limit, and if we're going to show that, then we should plug in our function, we should plug in our proposed limit, and we should plug in our a value. So here for epsilon, our function is 2x, our proposed limit is 4, that's epsilon, and the point at which we're taking the limit is 2. Should be less than delta. And the way you go about proving these is you try to find some relationship between epsilon and delta. And what I'm immediately noticing here is that 2x minus 4, we can factor out a 2 here. And we get 2 times the absolute value of x minus 2. It's less than epsilon. If we divide both sides by 2 here, we get the absolute value of x minus 2 is less than epsilon over 2. And this looks strikingly similar to the inequality that we have here with delta. And so if we say that delta is equal to epsilon over 2, then we can plug that in over here And we would have the absolute value of x minus 2 is less than epsilon over 2. Here we're simply plugging in our expression for delta to this equation. And if we work backwards, we will get absolute value of 2x minus 4 is less than epsilon. And so what we've just proven is that as long as delta is less than or equal to, it doesn't have to be epsilon over 2, it could be any number less than that. As long as delta is less than or equal to epsilon over 2, then the absolute value of 2x minus 4 will always be less than epsilon. And therefore, the limit exists. Because no matter how small we make epsilon, no matter how small this value becomes, there will always be some value delta, which will just be epsilon over 2, that will satisfy both these inequalities. Now, let's think about what that looks like on this graph, for example. Let's just say that we have a number of epsilon, or a value for epsilon of 1. That means that we will be looking for y values that are within 1 of our proposed limit. So here we would have a y value of 5, and we would have a y value of 3. Using the association that we derived, the delta values that will give us the x domain with which these y values will be routed to, the delta value here is going to be epsilon over 2, which is just 1/2. And so here we would have 2.5, and here we would have 1.5. And if you look, 1.5 times 2 is 3. That's just plugging into our function. And 2.5 times 2 is 5. So, like we say in here, as long as delta is less than epsilon over 2, as long as delta gives us x values that are within these bounds, they will always route to the y values within these bounds. And that's true for any epsilon as long as delta is less than or equal to epsilon over 2. So now let's take a look at an example that's just a little bit more complicated, just to see if we really have a handle on this definition. Let's say we're tasked with proving that the limit as x approaches 6 of 2x squared minus 24x plus 75 is equal to 3. If you plug this into a calculator with the number 6 or work it out by hand, you'll see that it does indeed equal 3, but we want to prove that the limit as x approaches 6 equals 3. And so just like before, we're wanting to show that for any value, for any epsilon greater than 0, there exists some delta greater than 0 such that the absolute value of f of x minus L is less than epsilon, and the absolute value of x minus A is less than delta. And if we plug in our f of x, our proposed limit, and our A value here, we'll get that for this inequality we'll have absolute value of 2x squared minus 24x plus 75 minus our proposed limit, which here we're saying is 3. It's less than epsilon. And here we have absolute value of x minus 6. It's less than delta. Working this out, 75 minus 3 is 72 plus 24x, 2x squared, absolute value here. Here you can factor out a 2. X squared minus 12x is 36. It's an epsilon. Now this looks to me like a perfect square polynomial. So we just have x minus 6 squared. Absolute value of that times 2 is less than epsilon. Here what we can notice is that x minus 6 squared is always going to be a positive number no matter what x minus 6 is. When you square that, it will be positive. So we can get rid of these absolute value bars. And here we have x minus 6 is less than epsilon over 2 the square root. And now we have something that looks similar to what we have over here. So if we let our delta be less than or equal to the square root of epsilon over 2, then we can plug that in here and see what happens. Have the absolute value of x minus 6 less than square root of epsilon over 2. We could square both sides. Squaring both sides, if I square the absolute value of x minus 6, that's just going to be the absolute value x minus 6 squared. Epsilon over 2. Then we multiply both sides by 2. We get the absolute value of 2 times x minus 6 squared, which is 2x squared minus 12 times 2 is 24x. And then we get 36 times 2 is 72, plus 72. It's less than epsilon. And we can rewrite this as plus 75 minus 3. That's equal to the same thing. 4x plus 75 minus 3. It's less than epsilon. And so here what we notice is that we can write it all out. Show where it's coming from. As long as delta is less than or equal to the square root of epsilon over 2, if delta is less than or equal to the square root of epsilon over 2, and this you will always be able to do because from our formal definition, epsilon must be greater than 0. So there's never going to be an imaginary number here. You will always be able to take a square root. If delta is less than or equal to the square root of epsilon over 2, then these inequalities will be satisfied. The absolute value of 2x squared minus 24x plus 75 minus 3 will be less than epsilon. And the absolute value of x minus 6 will be less than delta. And therefore, the limit at that point exists. And I implore you to graph it out, take a look at the bounds, and see that it does indeed work. The other thing that's pretty important that tends to come up when we're learning about limits are limit properties. So we're going to walk through most of those today and see if we can prove all of them, make sure we're comfortable knowing where those properties are coming from, comfortable that we have the proofs for each of them. So let's start with a pretty simple one. We can imagine a function. We'll just write it out. The x and y axis again. And we can imagine a function that's just a horizontal line, and we'll call it y is equal to f of x, which is equal to c. And c is just some constant, doesn't matter what it is. This function here will be just a straight horizontal line. And we can imagine that the limit of this function, as x approaches any number, we'll just say a of c, we can imagine that the limit of this is going to be c. And in general, it doesn't matter where you are on the x-axis. It will always route to a y value of c. So really, if we think about this, delta could be whatever we want. It could be 1,000,000 because it doesn't matter. It will always route to y values that are within epsilon of our proposed limit, as long as our proposed limit is the value c. And indeed, it will always route to c itself. It won't even need to be within a certain range. Epsilon can be as small as you want, and delta can be whatever you want, and it will always route properly and satisfy both of the inequalities. And if we actually go through the math, and we do our steps, do the absolute value of f of x minus L must be less than epsilon, and the absolute value of x minus a must be less than delta. When we plug in our proposed limit of c and our function of c, we'll see that we get c minus c here less than epsilon. Well, that's just 0. 0 is less than epsilon. And so what we see is it doesn't really matter what delta is. As long as epsilon is greater than 0, both of these inequalities will always be satisfied. So that's our first limit property. The limit of a constant is just that constant. The second property is also pretty simple. We say that the limit as x approaches a of x is equal to a. And if we work this out, I'm going to show that the absolute value of f of x minus L is less than epsilon. There will always be some delta associated such that the absolute value of x minus a will be less than delta. If we plug in our numbers here, f of x is going to be just x, and our proposed limit is going to be a. And what we notice is that this looks strikingly similar to our inequality with delta here. And so if we say that if delta is less than or equal to epsilon, then the absolute value of x minus a will be less than epsilon, and the absolute value of x minus a will be less than delta, and this property is true. Now we should move into some real properties that take some proving. So let's imagine that we have a limit given, and we know that the limit as x approaches a of f of x is equal to some value L. We know that this is true. This is assumed. We want to show that the limit as x approaches a of c, which is just any constant, times f of x, is equal to c times the limit of f of x, which we established is L. If we know that the limit as x approaches a of f of x is equal to L, then we know that for any value of epsilon, the absolute value of f of x minus L will be less than epsilon, and the absolute value of x minus a will be less than delta. So we can imagine that there must be, if this is true for any value of epsilon, there must be some delta, we can call it delta 1, such that the absolute value of f of x minus L is less than epsilon over the absolute value of c. We know that this is true because this limit exists. For any value of epsilon, no matter how small, there will always be some delta that we can find which will produce y values within the domain of epsilon of the value L, including an epsilon value of epsilon over the absolute value of c. So we know that this is true. We'll call that delta 1. So if we go through our process here, we have the absolute value of f of x minus L, f of x here being c times f of x, and our proposed limit here being c L less than epsilon. Here we can factor out the absolute value of c times the absolute value of f of x minus L less than epsilon, and now we can divide both sides, and we get that the absolute value of f of x minus L is less than epsilon over the absolute value of c. And we know that this is true. We just have to choose delta 1s, or we just have to choose delta such that it's less than or equal to delta 1. Then both of these inequalities will always be satisfied, which we showed here. So we could say that if delta is less than or equal to our delta 1 here, then the absolute value of f of x minus L will be less than epsilon over the absolute value of c. Or more succinctly, we should say if delta is less than or equal to delta 1, then the absolute value of c times f of x minus cl is less than epsilon, and the absolute value of x minus a is less than delta. That's more proper and proves this property here. Next property we're going to show It's going to get a little bit more complicated, still pretty simple. Provided that the limit as x approaches a of f of x is equal to L, we know this is assumed, and the limit as x approaches a g of x is equal to k, this is also assumed. We want to show that the limit as x approaches a of f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x, which is just L plus k. In order to go about proving this, we first need to understand something called the triangle inequality. This tells us that the absolute value of anything, say A, plus the absolute value of something else, say B, this is always going to be greater than or equal to the absolute value of A plus B. The reason being, if either one of these numbers are negative, this value here is going to be less. Or I should say, if either one of these are opposite signs, this value will be less. And if they're not opposite signs, then this will be equal to this. So the absolute value of A plus B is always going to be greater than or equal to the absolute value of A plus B. Knowing this, we can move forward. If we know that the limit as x approaches a of f of x is equal to L, then we know that for any value of epsilon, there will always be some value of delta that will satisfy the inequality's absolute value of f of x minus L less than epsilon. We could say that there would be some delta, we can call it delta 1, such that the absolute value of f of x minus L will be less than epsilon over 2. We can go by the same reasoning for g of x, and we could say that for delta 2, just call it delta 2, there would be the same case. The absolute value of g of x minus k is less than epsilon over 2. Now we can try to deal with this. If we try to write our inequalities for this, we want to show that the absolute value of f of x plus g of x minus the L plus k that we have there, our proposed limit, is less than epsilon when absolute value of x minus a is less than delta. We can rearrange this. We can factor out our negative, and then we can rearrange things. We would have the absolute value of f of x minus L plus g of x minus k is less than epsilon. And from our triangle inequality, we could write that the absolute value of x minus L plus g of x minus k is going to be less than or equal to the absolute value of f of x minus L plus the absolute value of g of x minus k. And if we say that delta is less than or equal to the minimum, whichever one is smaller, delta 1 and delta 2, which we established before up here, then we could say that this sum here is going to be less than epsilon over 2 plus epsilon over 2, which is just epsilon. And if this expression here is less than or equal to this, which is always less than this, it's safe to say that this is going to be less than this. And therefore, we have that the absolute value of f of x plus g of x minus k plus L is going to be less than epsilon if delta is less than or equal to the min of our delta 1 at delta 2, which we discussed up there. So the addition property is going to be true for limits. And for subtraction, it's a lot easier now that we've proven the addition one. if we have the same case here, we have the limit as x approaches a of f of x is equal to L limit of g of x is equal to k. If we know this, then we could say that the limit as x approaches a of f of x minus g of x is simply equal to the limit as x approaches a of f of x plus negative g of x. This is the same as the limit of f of x plus the limit of negative g of x, limit of f of x being L, and the limit of negative g of x, this is just g of x being multiplied by a constant, negative 1, which we already proved earlier is the same as that constant, negative 1, multiplied by the limit of that function. So this is the same as L plus negative k, which is equal to L minus k, and so therefore it holds for subtraction as well. So now we're going to talk about multiplication. Once again, it's going to get a little bit more complicated, but nothing we can't handle. Basically, we're going to start with the same presuppositions, that the limit as x approaches a of f of x is equal to L, this is assumed, and the limit as x approaches a of g of x is equal to k, this is also assumed. And we want to show that the limit as x approaches a of f of x times g of x is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x, which would just be L times k. So there's going to be a couple parts to this. The first step is, if we know that the limit as x approaches a of f of x is equal to L, then we should know that the limit as x approaches a of f of x minus L, we just showed that the limit of this is equal to the limit of this minus the limit of this from our subtraction property. So we could say that this is equal to the limit as x approaches a of f of x minus the limit as x approaches a of L. This is just a constant, and the limit of this is L, so this is equal to L minus L, which is equal to 0. So we showed that the limit as x approaches a of f of x minus L is equal to 0. We also know that the limit as x approaches a of g of x minus k will be equal to 0 by the same exact reasoning. And if we know this, then we can say that there must be some, if we know that this limit exists, then there must be some delta value, which we'll call it delta 1, where f of x minus L, that's our function, minus the limit, which we're saying is 0, we've proven is 0, it's going to be less than the square root of epsilon. And we're going to say when delta is less than or equal to delta 1. And this minus 0 is going to go away by the same reasoning. Absolute value of g of x minus k will be less than the square root of epsilon when delta is less than or equal to some other value. We'll say it's delta 2. This is going to come back into play a little bit later. Now what I'm going to do is just a little bit of algebraic manipulation. If I take f of x minus L and multiply it by g of x minus k, I'll get f of x times g of x minus k f of x minus L g of x plus L k. And now here I notice that this is what we're wanting to take the limit of. And this is something that looks remarkably close to what we have up here, right? F of x minus L and g of x minus k. And so if I can get this in terms of this and these other things, then I might be able to find a way to prove this property. And so I'm going to do that. I'm going to isolate f of x times g of x. I'll find that that's equal to f of x minus L times g of x minus k plus k f of x plus L g of x minus L k. And now, can I take the limit of this? Well, I can deal with this addition and subtraction because we already proved that that's a property of limits. If I'm taking the limit of this, it's going to equal the limit of this expression plus the limit of this one plus the limit of this one minus the limit of this one. We already proved that. But we still can't really move forward until we can prove what the limit of this expression here is, because we haven't shown any properties of limits yet that deal with multiplication. That's what we're trying to prove here. So if we can find out what the limit of this is, then we can move forward. And if we know that the absolute value of f of x minus L times the absolute value of g of x minus k is provided that delta is less than or equal to delta 1, or sorry, provided that delta is less than or equal to the minimum of delta 1 and delta 2, then we know that this is going to be less than the square root of epsilon times the square root of epsilon, which is equal to epsilon. And the absolute value of this times the absolute value of this, that's always going to be positive. Right? This is going to be positive, multiplied by this, it's going to be positive. If this was negative and it was multiplied by this, what I'm saying is this is going to be equal to the absolute value of f of x minus L times g of x minus k. We can move these two things together, because if one of these expressions was negative and it was multiplied by this one, or if they were opposite signs and this wound up being negative, it would be undid by these absolute value bars. You don't need separate ones over each of the expressions. And so if we know that this is less than epsilon, provided that delta is going to be less than or equal to the minimum of delta 1 and delta 2, then we can rewrite this a little bit, say that the absolute value of f of x minus L times g of x minus k minus 0 is less than epsilon, provided that delta is that. And basically what we've done here is we've proven that the limit as x approaches a of f of x minus L times g of x minus k, we've proven that that is equal to 0. Now that we've done that, we can return to our expression here, and we're finally ready to take the limit. When we take the limit of f of x times g of x, or all of this stuff over here, as x approaches a, this is going to go to 0, and then we're going to add k times the limit of f of x, which is just k times L. We're going to add L times the limit of g of x as x approaches a, which is just k. So KL plus LK, that's 2KL minus LK, is just equal to LK. And that proves that you can multiply limits. The hardest one of these to show is definitely the division property, which says that if we know that the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to k, then we want to show that the limit as x approaches a of f of x over g of x is equal to L over k. And if you think about this, this is really just the process of showing that the limit as x approaches a of 1 over g of x is equal to 1 over k. That's really all we need to show, because then after that, it's just a matter of the property of multiplication, which we already proved. Then it will just be f of x times 1 over g of x, and if we know the limit of 1 over g of x is 1 over k, and the limit of f of x is L, then we know that the limit of those two things multiplied together will be L over K, and we will have enough to sufficiently prove this property. But proving this right here is hard, and we're going to go through that. So first, we're just going to take this and say, okay, well, we're trying to show that the absolute value of 1 over g of x minus 1 over k is less than epsilon. We're trying to find some value of delta such that this will always be true, some relationship between delta such that this will be true for any epsilon. And we can start by sort of manipulating this a little bit algebraically. Find a common denominator. Seems like a good place to start. So we have k minus g of x over k times g of x. It's going to be an epsilon. Actually, I'm just going to leave off the epsilon for now and just deal with this expression because we're going to have to manipulate a little bit in order to prove this. Now what I'm seeing is that sort of how we can kind of pull this apart up here, we can pull apart this. When you have the absolute value of this over this, this is going to be equal to the absolute value of, or 1 over the absolute value of k times g of x times the absolute value of k minus g of x. The reason being is that if this numerator is positive or this denominator is positive or negative, it really doesn't matter because it's all going to be undid by the absolute value bars. It will always be positive. And as long as we maintain absolute value bars across each one of these things that are being multiplied by each other, then this is always going to be positive and it is equal. We can do that again with this right here. We can say that this is equal to 1 over the absolute value of k times 1 over the absolute value of g of x. And then with this is just the difference between k and g of x. And when you put the absolute value bars here, it's basically always just going to give us the magnitude of the difference between these two values. It's always going to be a positive number. And so that's going to be the same as the absolute value of g of x minus k. Think about it, if k was 1 and g of x was 5, it doesn't matter if it's 1 or negative 5, it doesn't matter. If you switch these two, the difference between those numbers will always be the same after you took those absolute value bars. So this is equal to this. Now we're going to step back a little bit because we have to find some way to make it to where that this is less than epsilon. We have to find some delta that will make this less than epsilon. And so in order to do that, we're going to take a step back and we're going to go to the absolute value of k itself. We can algebraically manipulate this as well. We can say that this is the same as the absolute value of k plus g of x minus g of x. It's just the same as adding 0. And we know from our triangle inequality that this is the same thing as, or not the same thing, but that this is going to be less than or equal to the absolute value of k minus g of x plus the absolute value of g of x. Those are going to be, this will always be less than or greater than or equal to this from the triangle inequality from before. And if we know that, well, this is just the same as absolute value of g of x minus k plus the absolute value of g of x. This once again being from this absolute value bar just measures the magnitude of the difference between these two numbers, so it doesn't matter which one is being subtracted from which. It's not going to change the resultant absolute value. So we can say that the absolute value of k is going to be less than or equal to that. And now if you notice, this expression here, the absolute value of g of x minus k, that looks strikingly similar to what you would find if you were to play around with this limit with the formal definition. The limit as x approaches a of g of x is equal to k. Well, that tells us that there will always be some delta value which will make the absolute value of g of x minus k less than epsilon, no matter how small that epsilon gets. And armed with this information, we can think of a value for epsilon that we can basically get rid of this expression and just have an expression for g of x. And one thing that I could think of would be if delta is less than or equal to delta 1, then the absolute value of g of x minus k, we could say would be less than the absolute value of k over 2. And then if we say that if delta is less than or equal to delta 1, then this expression, absolute value of k, will be less than, not less than or equal to, the absolute value of k over 2, which we just showed, plus g of x. And now we can solve this for g of x, because you just subtract this from both sides. That's the absolute value of k over 2 is less than g of x. And now what we can do is we can take the inverse of this. And when you take the inverse with an inequality, you have to flip it. That's so. The reason being, if this number is greater than this one, then 1 over this number will have to be less than this one. And that should make sense. And so now we know that 1 over g of x is going to be less than 2 over the absolute value of k when delta is less than or equal to delta 1. And so this expression here, 1 over the absolute value of k times 1 over g of x times the absolute value of g of x minus k, this is going to be less than 1 over the absolute value of k times 2 over the absolute value of k, which is just 2 over the absolute value of k squared, times absolute value g of x minus k. And that's when delta is less than equal to delta 1. Okay, so we've made some progress here. We've got rid of 2 terms and turned it into just 1, but now we need to get rid of this one. And I'm noticing here that the absolute value of g of x minus k, well, once again, that looks strikingly similar to what you would get in an inequality given this limit here if you were to look at the formal definition of that. So we're going to do the same thing again. If I know that the limit as x approaches a, g of x is equal to k, then that means that for any value of epsilon, no matter how small, there will always be some delta that will satisfy this inequality and the absolute value of x minus a being less than delta. And so we could say that this is going to be less than, and then if we want to get rid of this, we would just say the absolute value of k squared over 2 times epsilon when delta is less than or equal to delta 2. And now what we can say is that 1 over the absolute value of k times 1 over g of x times the absolute value of g of x minus k is going to be less than 2 over the absolute value of k squared times k's absolute value of k squared over 2 epsilon when epsilon or delta is less than or equal to the minimum of delta 1 and delta 2. When delta is less than or equal to the minimum of those 2 deltas, then we're going to get this. This expression right here we derived all the way back from the beginning from 1 over g of x minus 1 over k. And so this is just equal to the absolute value of 1 over g of x minus 1 over k. And we just showed that this is going to be when delta is less than or equal to the minimum of delta 1 or delta 2. This is going to be less than this, which these 2's are going to cancel. This absolute values are going to cancel. Absolute value of k squareds are going to cancel is what I meant. And it's going to be less than epsilon when delta less than or equal to the minimum of delta 1, delta 2. And so we have just proven that the limit of 1 over g of x is equal to 1 over k. And now that we know that, we know that the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x times 1 over g of x. That is the same thing, and this is equal to L times 1 over k, which is just equal to L over k. So there you have it. That quotient rule was proven. I know that one was a bit of a doozy, but we made it through. Alrighty, we got one property left to get through, and then we'll have proven all the limit properties that I'm aware of. At least finite limit properties. This proof is going to use proof by induction, and so I'm going to go over an example of a different proof for a completely different concept, just to sort of get you guys familiar with the concept of proof by induction. And so if we have a sequence that's defined S of n, and this is just going to equal 1 plus 2 plus 3 plus n. This is the sum of all integers up to n. That's what this function here yields, the sum of all integers up to n. We want to say that S of n is equal to n times n plus 1 divided by 2. We are postulating that this is true. How can we prove this? Well, one thing I can show is that this is true for 1, because the sum of all integers up to 1 is just going to be 1. And if we use the formula here, 1 times 1 plus 1 divided by 2 is just 1 times 2 divided by 2. Those are going to cancel. This is equal to 1. So certainly this formula is true for 1. And so proof by induction is going to say, I'm going to assume that this is true for some value k. We're going to assume that this is true. So this is going to be assumed true. And then we're going to say that the sum function that we're dealing with for k plus 1, the next integer in the list, if we can show that this follows the formula, then we will be in business. Because if we can show, if we assume that this is true and we know that this is true, then this can become the next k, and then the next number will be true, and we'll know that this is true for all numbers. And so what is this going to equal? Well, if we work it out, this is just going to equal the sum of all numbers up to k plus 1. Right? That should seem logical. This will equal the sum of all numbers up to k plus the next number in the sequence, which is just k plus 1. And the sum of all numbers up to k is, we assume this is just equal to k times k plus 1 over 2, k times k plus 1 over 2, plus k plus 1. And if we find a common denominator here, this is just 2 times k plus 1 over 2. So this is equal to k times k plus 1 plus 2 times k plus 1 divided by 2. And what we find here is that we could say that this is equal to k plus 1 times k plus 2, k and the 2 here, divided by 2. And that is the same as plugging into the formula here. If we say that the sum k plus 1 is equal to we know that this is true, but if we use the formula n times n plus 1 over 2, we're going to get k plus 1 times n plus 1, which is going to be k plus 1 plus 1, k plus 2, divided by 2. That's exactly the same thing. So we know that this is true. If this is true for k, or we assume it's true for k, and we know that it's true for k plus 1, then we could say for all k's, all the way to infinity, this is going to be true. This formula is going to hold true. And so all we need to do is prove, because we've already done this, all we need to do is prove that this is true for one value. And we already showed that it's true at 1. And so for all these things, we could say that the sum function that we're describing is going to equal n times n plus 1 divided by 2, proved by induction. And so just to recap, our goal here is to show, we're going to assume that this is true for one value k, and then show that it's true for k plus 1. These are meant to stay arbitrary because the new k plus 1, if it's true for that, then that could just become the next k. And then the k plus 1 after that will also be true. We know that because we've proved that it's true for k plus 1. And that will go on and on and on for infinity. And this will be true for all real numbers. Or in this case, all real integers. And then all we need to do is show that it's true for 1k. And then we know that it's true for all k's past that point. So that's the idea for proving something based on induction. And that's what we're going to do here. We know that the limit, as x approaches a, of f of x is equal to L. And we want to show that the limit as x approaches a of f of x to the power of n is going to be equal to the limit of this to the power of n, which is just L to the power of n. And we're going to prove this by induction. And so if n is equal to 1, then this is just going to say that the limit as x approaches a of f of x is equal to L to the power of 1, which is just L. And we know that that's true. The limit as x approaches a of f of x is L. We know that. And so we know that this is true. We know that this is true for n equals 1. And so because of that, we can assume that the limit as x approaches a of f of x to the power of n minus 1 is equal to L to the power of n minus 1. We're going to assume that this is true. And if that is true, then the limit as x approaches a of f of x to the power of n is equal to the limit as x approaches a of f of x to the power n minus 1 times f of x. If you multiply these, that will add 1 here and it will just become this. We are assuming that the limit of this is just equal to L to the power of n minus 1, and we know that the limit of this is just L, and so this will give us L to the power of n. And so if we're assuming that this is true, and we prove that it's true for, if we're assuming that this is true for n minus 1, and we show and we prove that it's true for n, given that n minus 1 is the case, then all we need to do is prove that this function is true for one value of n, that being n equals 1. And then we know that for all numbers greater than n equals 1, this value, this property must hold true. Proved by induction. And so just a little conclusion here. Just a conclusion here of everything we covered in this video. hopefully we explained the formal definition of a limit. Formal definition of a limit of a limit. We used the formal definition to prove limits of functions. And then we proved the following limit function, or limit properties. The following limit properties. We proved that the limit as x approaches a of c is equal to c. We proved that the limit as x approaches a x is equal to a. And then we proved, assuming c is a constant and the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to k. Then we proved that the limit as x approaches a of c times f of x is equal to CL. We proved the limit as x approaches a of f of x plus g of x, or I should say plus or minus g of x, is equal to L plus or minus k. We proved that the limit as x approaches a of f of x times g of x is equal to L times k. We proved that the limit as x approaches a of f of x over g of x is equal to L over k. And we proved that the limit as x approaches a of f of x to the power of n is equal to L to the power of n. It's a terrible n. Let's redo that. Boom. And so that is what we covered in this video. We explained the formal definition of the limit. We use the formal definition to prove limits of functions. We prove the following limit properties. Limit of a constant is that constant. Limit of x approaches a of x is a. And then assuming c is a constant, and that the limit as x approaches a of f of x is L, and that the limit of x approaches a of g of x is k, we prove that the limit as x approaches a of a constant times f of x is just the constant times the limit of that function. We proved the limit as x approaches a of two functions being added together is just the sum or difference of the limits of those two functions. We proved the same with multiplication, the same with division, and with exponentials. And so hopefully you can go through and do all of these steps yourself, and hopefully this gives you a little bit of an explanation as to where these properties come from, an explanation as to what a limit actually is, and hopefully it deepens your understanding of mathematics.